Thank you very much. Thank you very much for giving me an opportunity to talk. It's my great pleasure to give a colloquium talk. So here's my title, the Bruhat interval polytopes, which are cubes. But precisely speaking, this cube is not exactly cubes. I mean that it is combinatorially equivalent to cubes. Okay, anyway, so this is a joint. This talk is based on joint work with Eunjung Lee and Sanjay Park. Okay, and if you have any question, please ask during my talk. Otherwise, I feel uneasy because I'm just speaking to my computer. Okay. So here's the content of my talk. Since this is a colloquium talk, I'll start with permutohedron, which is very familiar, polytope, and then I introduce Bruhat interval polytope. This Bruhat interval polytopes was introduced 2015, so 5 or 6 years ago by Kodama and Williams and also Tsukama. So this is Bruhat interval polytope is a rather new subject or object. Then I will talk about toric Richardson varieties of Catalan type and polygon triangulations. So this is the third section is the main part of this talk. And then our result is related to Wedderburn-Etherington numbers. So I will talk about that numbers. Okay, so let me start with permutohedron. As you know, the permutohedron, first the Sn, this Sn is a symmetry group on n letters, and the Pn is a convex hull or points in Rn, so associated to the permutations. So, okay. And this Pn is called permutohedron. So this is the case when n is 3, the hexagon. So this P3, and so this is a P4. And so Pn lies on a hyperplane because the sum of coordinates here is independent of the permutation W. So Pn lies on the hyperplane, so that the Pn is the dimension of Pn is at most n-1, but actually the dimension of Pn is exactly n-1. Okay, and the vertices of the permutohedron correspond to bijectively to the set of the symmetric group. So the number of vertices of Pn is n factorial, and Pn permutohedron is simple. That means since this is n-1 dimension, there are exactly n-1 edges emanating from each vertex. For instance, look at this picture. This is a three-dimensional permutohedron. So at each vertex, there are exactly 3 edges emanating. And this permutohedron is very well studied. For instance, the phase structures are well understood. And the H polynomial, it is known that H polynomial agrees with Eulerian polynomial, and the volumes of Pn is understood, and so on. There are many researches on Pn. So Pn permutohedron is an interesting convex polytope from the viewpoint of combinatorics, but not only that, it is related to geometry. So that I'm going to explain next. So relation of permutohedron to geometry. So I remind you, I'm not sure everybody knows Frag variety, but so anyway, I remind you the definition of Frag variety. So Frag variety is a set of frags, and the frag means nested sequence of linear subspace of Cn, C to the n. So these Bk, B1, B2 are linear subspace of Cn. And the dimension of Bk, complex dimension of Bk is k, for any k. And so there is a natural surjection from the general linear group to Frag variety, such that that pi is defined this way. So this is a non-singular matrix, and I take a first column and then take the line spanned by A1, the first column. And then I take the first and second columns and take the linear span of the first and second columns. And since A1, A2 are linearly independent, this span is two-dimensional. And then I take the first and second and third columns and take the linear span, its linear span, and so on. This is how we get the frag, how we get this map pi. Okay, and it is easy to see that if you are given two matrices, non-singular matrices A and B, if their image, pi image, the same, then A and B have this relation, so they are same up to multiplication by upper triangular matrices from the right. So that the dimension of general linear group, this is n squared dimension, complex dimension. And the dimension of the group consisting of upper triangular matrices is 1/2 times n plus 1. So that the dimension of Frag variety is n squared minus 1/2 n times n plus 1. So that is this number. So we can see the dimension of the Frag variety easily. And one more important thing is that there is what is called moment map from the Frag variety to the permutohedron. This is a surjective map. I'm not going to give the definition of moment map, but anyway, there is such a map. So, and Gelfand, Selganova, they studied T orbits in this Frag variety in 1980s, where T is the diagonal torus in general linear group. I mean diagonal matrices. This T is the diagonal matrices, so that T is C star torus. C star means C minus origin. Okay, and as I said, I'm not going to give a definition of moment map, but I give you some feeling about moment map. So the simple or simplest example of a moment map is a height function on the two-dimensional sphere. So you have a sphere and consider height function. So the south pole is height 0, and north pole is height 1. Okay, and equator is height 1/2. So that the image of S2 by the height function is a 0-1 interval. Okay, this is a typical and the simplest example of moment map. And if you take n-fold product of this map, then you get a map from S2 n-fold product of S2 to n-fold product of interval. So n-fold product of interval is nothing but n cubed. So this is how we get a map from the manifold or variety to a convex polytope. So this moment map, you can think of a moment map as a generalization of this example. Okay. Now I introduce Bruhat interval polytope. So before that, I need to remind you the definition of Bruhat order. There are several definitions of Bruhat order. So I give you one definition. So for a finite set of integers, actually I consider the finite set of natural positive integers. Let's say 9, 2, 7, 4. And then we define this notation, up arrow. So this means I arrange these elements in this set in an increasing order. So 2, 4, 7, 9. Okay, and I need to introduce one more notation. I take two tuples of integers, and I give you a partial order on k-tuple of integers. So the definition is simple. So I compare each ith entries. If ai is less than or equal to bi for all I, then this k-tuple is less than or equal to this k-tuple. And now I come to the definition of Bruhat order. So for two permutation V and W, so we define V is less than or equal to W if and only if. So I look at the first k numbers of these permutations, V1, Vk, and also first k numbers of W, W1, and Wk, and I arrange them in an increasing order. And if this inequality holds for any k, then we say that V is less than or equal to W. So this is a partial order on the symmetric group. And this is called the Bruhat order. And here's the example. So I take two permutations. This is one line notation on permutation. And first, let's look at the first entries. Here 2 and 3. And 2 is less than or equal to 3. And look at the first two numbers, 2, 3, and 3, 2. And I arrange them in increasing order. Then 2, 3, and 2, 3. We have this inequality. And take first three numbers and arrange it increasing order, and then I get 1, 2, 3. Here 3, 2, 4. So I arrange it in increasing order. I get 2, 3, 4. We have this inequality. So because of this observation, so we have this inequality. But so if I take similar permutations, and I do the same thing, then look at the first entries, and 2 is less than or equal to 3, and look at the first two entries and arrange in increasing order. The first one is 2, 4, and this is 2, 3. 2, 3. This 2, 4 is not less than or equal to 2, 3. So that this permutation is not less than or equal to 3, 2, 4, 1. Okay, so here is a, I think many of you have seen this Hasse diagram. So this is a Hasse diagram of F3, and this is a Hasse diagram of S4. So identity element is the smallest element. Okay. And the length, so length of permutation is, let's say, so length of this permutation is, we look at the path from the identity element to this permutation. So for instance, this path, so there are two edges. So that the length of this permutation is 2. And the length of this permutation, so I look at the, for instance, look at this one, this path. So there are 3 edges, so that the length of this permutation is 3. Or you can define the length of permutation by looking at the number of inversions of permutation. So anyway, this is the Bruhat order. And the Bruhat interval is, so the Bruhat interval BW. So I take all permutations between B and W. So this is the Bruhat interval. For instance, if B is this one and W is this one, then Bruhat interval is consists of 4 elements: this. Okay. Now I introduce Bruhat interval polytope. So as I said, this was introduced by Kodama Williams and Tsukama Williams in 2015, and they studied, especially Tsukama Williams, they studied the Bruhat interval polytope from combinatorial viewpoint, and Kodama Williams was interested in this Bruhat interval polytope from the total lattice, which I don't know much, but anyway, so this is a new object, and the definition is quite simple. So I take a pair of permutations with this inequality in Bruhat order, and I look at all elements in the Bruhat interval Z, okay, and take points in Rn associated to Z, and then take the convex half. So if B is identity and W is maximal element, then so this Bruhat interval polytope is nothing but permutohedron, because all elements appear in that case. Elements of permutation appear in that case. So the definition is quite simple, but for instance, if you take, let's say B, this is B, 1, 3, 2, 4, and the W is, let's say, can you see the 4, 2, 3, 1, and then in between, these elements, there are many permutations. This, okay, and then we take the convex half, then we get this this polytope. This is an example of Bruhat interval polytope. And you see, this edge is not the edge of permutohedron. This edge is edge of permutohedron, but this edge is not. But this edge is parallel to the edge, to an edge of permutohedron. So any edge of Bruhat interval polytope is parallel to some edge of permutohedron. And also, vertices. Vertices are permutations. Okay.
I have a question. I'm sorry,
Yes.
I have a question.
Yes.
So if you take, in your construction, you take the standard permutohedron when vertices are obtained from 1, 2, 3, etc., and all permutations. But if you take other numbers and permute them, and
Yes.
take the same definition of Bruhat about polytope, is it the same combinatorially?
I think if you take, let's say, the different, take a vector in Rn, each component is different, and then I think what you do is permute coordinates.
Yes.
Not permute numbers. Huh?
Yeah. Permute coordinates, but then geometry of the permutohedron itself is kind of different. So if you take some other
geometry is different, but combinatorial structure is the same.
Yeah, right.
So the Bruhat interval polytope also the combinatorial structure same.
Same. Yeah. Thank you.
Yeah. Okay, and as I said, Zuckerman, Williams studied combinatorics on Bruhat interval polytope, but for instance, they showed that any face of Bruhat interval polytope is a Bruhat interval polytope. And also they, they found a formula to give the dimension of Bruhat interval polytope. But there are many things to be studied, I think. For instance, it is unknown when this Bruhat interval polytope is simple. So look at this one. This is not a simple polytope. For instance, here look at this vertex. This is three-dimensional polytope, but there are 4 edges emanating from this vertex. So this is not simple polytope. But we have a conjecture that this Bruhat interval polytope is simple if and only if the vertices P and W are both simple. So, okay, so B is in some sense a bottom, and W is the top point. Right? If these 2 points are simple points, then the other points, other vertices, must be simple points. So this is our conjecture, and we checked this conjecture for small, for Bruhat interval polytopes of small dimension. I think up to 4 or 5 dimensions. Okay, so anyway, what I want to say is I think there are many things to be studied about Bruhat interval polytopes. And the Bruhat interval is a Coxeter matroid. Also, Bruhat interval polytope is a Coxeter matroid polytope. Okay, so I remind you the definition of Coxeter matroid. So subset of the symmetry group is called Coxeter matroid if for each U in the symmetry group there exists a unique element, let's say M, in this subset M, such that X is less than or equal to M. This with this inequality for all X. So in other words, and this inequality means this one. This inequality is in Bruhat order. Okay, so this inequality, like U-shifted Bruhat order, and the Bruhat order, the identity element is minimum element. But with respect to this partial order, U is minimum. Okay, because of this definition. So anyway, so with this, for each U, we have this partial ordering. and M has a unique maximum element with respect to this partial order. So this M depends on U, of course. So this is the definition of Coxeter matroid. And every Bruhat interval is a Coxeter matroid. And the Coxeter matroid is defined more generally for subset of W quotient by parabolic subgroup P. So W is a Coxeter group, and P is a parabolic subgroup of W. So here I take P is a trivial, identity W is Sn. And the Coxeter matroid polytope is the convex hull of Coxeter matroid. So, and if M is the entire set, Sn, then it is a Coxeter matroid. So the permutohedron is a Coxeter matroid polytope, and the Bruhat interval polytope is also Coxeter matroid polytope. And this definition is not easy to understand, but there's a nice characterization of Coxeter matroid by Gelfand and Selganova. Their result is the following. A subset M of Sn is a Coxeter matroid if and only if every edge of the convex hull of M is parallel to an edge of permutohedron. For instance, okay, so these permutations, S3 has 6 elements, and for instance, the 1, 2, 3, and 3, 2, 1. So these 2 elements, the set consisting of these 2 elements, is a Coxeter matroid, because if you take the convex hull of these 2 points, you get this edge, and this edge is parallel to this edge. But if you take a subset consisting of 1, 2, 3, and 2, 3, 1, okay, then take the convex hull of these 2 elements, then you get this edge. But this edge is not parallel to any edge of permutohedron, this hexagon. So that the set of consisting of 2 elements is not Coxeter matroid. So this is very nice characterization of Coxeter matroid. Okay. So anyway, Bruhat interval polytope is a Coxeter matroid polytope. And also the relation, there's a Bruhat interval polytope is related to geometry. First dimension of Bruhat interval polytope, QVW, the real dimension, is less than or equal to the length of W minus the length of P. So length of a permutation is a number of inversion. For instance, length of 2, 4, 1, 3. So you look at the number of inversions. Here inversion is 2, 1 is the inversion, 4, 1, and 4, 3. There are 3 inversions. So the length of this permutation is 3. And as I said, there is a moment map from the flower variety to the permutohedron variety. There is a moment map from flower variety to permutohedron. And here, Bruhat interval polytope sits in permutohedron. And there is a geometrical object which is a subvariety of flower variety called the Richardson variety, corresponding to this Bruhat interval polytope. So XVW, its determined by pair of permutations. And if you restrict this moment map to this Richardson variety, it's subject, XVW subject to the Bruhat interval polytopes QVW. And the dimension of this Richardson variety is equal to length of W minus length of V. Okay? And the following facts can be proved, and the following facts motivated our result. So, as I said, torus T is acting on Cn. Torus T is a diagonal matrices, so that it acts on Cn, and that action induces an action on subvariety, and that action preserves Richardson variety XVW. So that you can talk about whether XVW is toric or not with respect to that torus action. And XVW is toric if and only if this the dimension of QVW is LW minus LV. In other words, the equality holds here. And XVW is toric and smooth if and only if this dimension condition is satisfied and this Bruhat interval polytope is simple. So smoothness implies simpleness, and this condition is equivalent to saying that this Bruhat interval polytope is cube. I mean, combinatorially equivalent to a cube. Here, you need some argument, but anyway, this is the reason why we got interested in the Bruhat interval polytope, which are cube. Okay. Now, so we come to the main part of this talk. So here is I've explained what we did by an example. So let's look at this Bruhat interval polytope. V is, let's say, 1, 2, 4, 3, and W is 2, 4, 1, 3. 2, 4, 3, 1. And then Bruhat interval polytope is this red part. This is cube. Okay, this is cube. And here the coordinate of vertex, let's say 1, 4, 2, 3, is 1, 4, 2, 3. It's a point in R4. And now, so I look at the vertex, this vertex, and look at the primitive edge vector. So there are 3 edges emanating from this vertex, and this direction, you can easily see that. So this point minus this point, okay? So that this direction is 1, so first coordinate is 1 because 2 minus 1, and second coordinate is 1 minus 2, that minus 1, and 4 minus 4 is 0, 3 minus 3 is 0. So that this direction is 1, minus 1, 0, 0. That's direction vector. And also that's primitive vector. So that this primitive edge vector in this primitive edge vector of this edge is E1 minus E2. And the primitive edge vector of this one you can check easily, E2 minus E3, and primitive edge vector of this edge is E2 minus E4. Okay? And also I do the same thing, easy computation show that the primitive H vector of these three edges are given by this vector. Okay, now I take the dual of these vectors, dual basis. So this is a basis, actually this is a basis of three-dimensional lattice. And then, so there are dual vectors. So the dual vectors is geometrically, it is a primitive normal vector to facet. Facet means, in this case, two-dimensional face. So that gives those normal dual vectors, the dual vectors are given as follows: B1, B2, B3, and here W1, W2, W3. So you can easily check that. So, okay, B1, this is, so I take the dot product or scalar product of these vectors. So you get 1 here, here you get 0, here you get 0. And with this vector, I take the product, scalar product, I get 0, here plus 1, and 0. And here 0, 0, plus 1. So these three vectors are dual basis of this vector, and these two. So these vectors, so these three vectors are facet normal vectors. I mean, the normal vectors, or probably normal vectors of some facet face. This has 6 two-dimensional face, and this is here we have 6 vectors. So each vector corresponds to one normal vector to a face. Okay, so I copied this one from the previous page. Okay, and primitive H vectors lie in the lattice capital M defined by sublattice of Z to the 4 with coordinates equal to 0. Because here, so they sit in here. So that, and these B and W are dual bases. So, and the dual space of M is a quotient of Z4 by the this line. Because this is M is a sublattice of Z4, but N is a quotient of Z4 by this line. So you can check you can easily check that they are dual through the dot product, scalar product. And as a basis of N, the following is a natural basis. So E1, so I take the image of E1 to N. I call it pi1. And pi2 is the image of E1 plus E2 to the N. And pi3 is the image of E1 plus E2 plus E3 to N. And E1 plus E2 plus E3 plus E4, its image in N is 0 because I'm taking the quotient by this vector. So pi4 is 0, and I set pi0 equal to 0 for convenience. So this pi1, pi2, pi3 is a natural basis of N. And now I write V1, V2, V3, also W1, W2, W3 by this basis. Then, so V1 is pi1 minus pi4, and V2 is pi2 minus pi3, and so on. So let's look at it. For instance, V2. V2 is minus E3. Minus E3 is pi2 minus pi3. This one is minus E3. So that if I express these B and W in terms of pi 1, pi 2, pi 3, I get this expression. Now, what I do is I look at the suffixes of pi here, V1. Suffixes are 1, 4. So I prepare a hexagon here and label vertices from 0 to 4, the same counterclockwise. And here label, suffixes is 1, 4, so that I connect vertex 1 and 4. So I get this edge, this diagonal. And here, 2, 3, and also I assign V1 to this diagonal. And 2, 3 here, so you get I connect 2 and 3 and assign this V2 here to this edge. And V3 and 3, 4, and connect 3, vertex 3 and 4, and assign V3 to this edge. And I do the same thing for W1, W2, W3. Then I get the triangulation of hexagon, pentagon. This is how we get the polygon triangulation from Bruhat interval polytope. And also, these V and W, they have relations. So V1 plus V2 is equal to 0 because this one, look at this one, and V2 plus W2 is what? Pi 1 minus pi 3. But pi 1 minus pi 3 is just W3. So I get this relation and this relation also. So these relations, for instance, look at this one, second one, and here V2 is here, W2 is here, and their sum is W3 here. So this relation corresponds to the triangle. So each relation corresponds to triangle. Okay, so what I want to say is that so I started with the Bruhat interval polytope, and I look at the normal vector, H vector, and facet normal vectors. And if you are familiar with toric theory, facet normal vectors give you facet normal vectors are important to define the fan. And here, what I want to emphasize is that this polygon triangulation contains all the information of the fan. So, in other words, this polygon contains all the information of toric, so that Richardson variety corresponding to the Bruhat interval polytope. So, okay. And this story holds for any pair satisfying these conditions. So our permutation was this one, 1, 2, 4, 3, and 2, 3, 2, 4, 3, 1. And this permutation, the pair of permutations, is very special. So W is just, so I moved the 1 to the end. Okay? For such a permutation, a pair of permutation, we can do the same thing. Okay, so we say that the toric Richardson varieties is of Catalan type when the pair of VW is of the above form. Now, because this is a very special pair of permutations. So now I remind you the Catalan numbers. I think many of you will know that. The Catalan number is this number, and that satisfies this recurrence relation. And it is known that these numbers count more than 200 different objects. If you see the standard book, Catalan Numbers, so this is the Catalan Numbers, up to 10. And there are 200, so Catalan number counts more than 200 different objects. So I give you 3 examples. So number of triangulations of n plus 2 bonds by adding diagonals which do not intersect in their interiors. So this is examples. Okay. There are 5 triangulations of 5 bonds. And also the number of binary trees with n vertices. And this is a case where n is 3. So binary trees, I think you know that. So at each vertex, there are at most 2 children. And their correspondence is easy. For instance, this one. So this root corresponds to this. So first I fix this edge. Okay. And then look at the triangle, which has this edge, and assign the vertex. So I assign the vertex to each triangle, but so this triangle, which contains this edge, is a special one, and the vertex corresponds to this triangle. It's a root, and here there are 2 triangles adjacent to this triangle, so that's why I connect vertices. Okay, this vertex corresponds to this one, this vertex corresponds to this one, this vertex corresponds to this one. Since they are adjacent, I connected these 2 vertices, and also these 2 adjacent, so I connected these 2. And do the same thing for others. And also, the number of different ways, so n plus 1 factors can be completely parenthesized. So for instance, I take n to be 3, so we have 4 letters, and I give a parenthesis, and then associativity, parenthesize, so that I get 5 ways. Okay. Now, so we got the polygon triangulation from the Bruhat interval polytope. So, and so that we get binary trees from the Bruhat interval polytope. But okay, so this binary trees correspond to this polygon triangulation, and this binary tree corresponds to this polygon triangulation. But if I deflect this polygon triangulation with through this vertical line, so I get this polygon triangulation. So that corresponds, this deflection corresponds to deflecting this binary trees along this edge. So just you did, I've said, you change left child, interchange left and right.
Excuse me,
okay, so yes.
Do I understand right that when you're saying binary tree, you mean a rooted binary tree?
Rooted, yes. Binary tree means rooted.
Oh, okay, thank you.
And also, so binary tree is rooted and ordered. So left child and right child. It's as I've said, specified. Okay. But here I want to say I say that unordered binary tree is a binary tree but without ordering. So these two are different as a binary tree, but they are isomorphic as an unordered binary trees. Also, if you can look at this vertex and interchange left child and right child. So they are isomorphic as unordered binary trees. Okay, so now here is our main result. So there is a bijective correspondence between the isomorphism class of n-dimensional toric Richardson varieties of Catalan type and isomorphism class of unordered binary trees with n vertices. Okay, and the number of the latter set, this set, is known to be equal to the Wedderburn-Etherington number Bn plus 1. So now I explain what Wedderburn-Etherington number. So Wedderburn-Etherington number Bn is the number of ways of parenthesizing a string of n letters subject to commutative but non-associative binary operation. And the Catalan number is non-associative, quite similar. Catalan number is quite similar. It's non-associative and also non-commutative. But here we assume commutativity. So B1, B2 is 1, it's easy. And B3, look at B3 is equal to 1. So we have 3 letters, star, 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 and then we put the binary operation. There are 2 ways. But since we assume the commutativity, so you can exchange the first these 2 and this one, just exchange, interchange, so that they are equal, they are same. So that's why B3 is equal to 1. And look at the B4. B4 is equal to 2 because so I take the 4 letters and put parentheses, right? Binary operation. There are 5 ways. This is Catalan number exactly, C3. But look at this one. So I can interchange this and this. Exchange, how to say exchange. Then I get this one. Also, then I can exchange this part and start the last one. Then I get this one. And then I interchange this part and this part. Then I get this one. So the last 4, these 4 are same. So that's why, but that's different. The first one is different from the others. So that's why B4 is equal to 2. And Bn, this sequence satisfies the following recurrence relations. And so using this recurrence relation, we know B1 is equal to 1, so that we can compute Wedderburn-Etherington number. So this is Catalan number, so that you see the C10 is this big number, but B10 is only 98. So Bn is much smaller than Cn. Now, so Wedderburn-Etherington number, and I compare the Bn with Cn. So there seems no explicit formula to describe Bn, while Cn is this one, as you know. And the generating function of this Wedderburn-Etherington number satisfies these functional equations. And this was the motivation of Wedderburn in his work almost 100 years ago, while the generating function of Catalan number is quite simple at this form. This function. And Wedderburn-Etherington numbers count several different objects. And our results add one new object, while the Catalan numbers count, as I said, more than 200 different objects. Okay, now, and problem and the summary of this talk. The problem, what I'm interested is to find all pairs BW permutations such that Bruhat about QVW is a cube. I don't know the answer, but there are many pairs BW such that QVW is a cube. For instance, when V is identity, and then W is a Coxeter element. Coxeter element is the product of simple, mutually distinct simple reflections. But otherwise, when V is not identity element, I don't know the answer. But I can see there are many pairs of VW, such that QVW is a cube. And what we did is we treated a very special case, extreme case. W is V times S1 times S2. So these are simple reflections, transpositions, or V Sn minus 1 times S2 and S1. And the difference of length is n minus 1. So in this case, the polygon triangulations appeared, or unordered binary trees appeared. But in other cases, since I don't have time, but in this case, Richardson varieties, toric Richardson varieties is Schubert varieties, and in that case, directed path appears in the classification of toric Schubert varieties. And also, so what we discussed is D type A. But in other D type, when V is toric Schubert varieties case, what we get is Dynkin diagram, and or precisely speaking, directed Dynkin diagram appears in the classification of toric Schubert varieties. So I stop here. Thank you very much for your attention.
Yes, Professor Masuda, thank you very much for the very nice talk. Now we have some time for questions. Please, if there are questions, you may write to chat or unmute yourself.
If I may ask a quick question.
Sure, absolutely.
So this is, I don't really know very much about Coxeter matroids. What is really comparison? For example, in ordinary matroids, it is hypersimplex, which serves as somehow the role of the permutohedron. So, and then of course these matroid polytopes are used in some sense to classify orbits, let's say in Grassmannians and so on. So I think you mentioned the result, but I forgot the names, that the orbits in the flag variety are also more or less classified by that. So is this completely settled? I mean, is it
not completely settled? No. I think the torus orbits in the flag varieties are not, not specified. And for instance, you take a torus orbit in the flag variety, and you take a closure. Actually, you take the closure of torus orbit and look at the moment map image. So it is Coxeter matroid polytope. But I think it is unknown that what kind of Coxeter matroid polytope appears as a moment map image of torus orbit closure. That's a kind of representability of Coxeter matroid polytope.
Thank
You
you.
understand?
Thank you. Are there more questions?
Yeah, I have a question. So you mentioned that so you consider this condition that all edges of this subpolytope are parallel to edges of permutohedron. Is it equivalent to saying that facets of the polytope are parallel to facets of permutohedron?
That I don't know.
If you take the edges parallel to permutohedron, it has something to do to the Minkowski. It is Minkowski summand or something like that. And about parallel faces, I don't remember at the moment, but well, I guess not. But yeah. Well, anyway, sorry.
Yeah, but at least at these low-dimensional pictures, I guess that all faces are also parallel to faces of permutohedron.
But it seems that if you take n-1 edges, then you can define the facet vector, is it?
Yeah, I also thought about some simple polytopes, so maybe in simple polytopes.
Simple polytope.
Yeah, if it is simple, then there is some correspondence between edges and faces. Yeah, but I don't know.
It is a meaningful question because it's really interesting. What is there are these deformations of permutohedra, these how they are called, generalized permutohedron of Postnikov and other people, and it is simply it is obviously related, but I guess these are more general objects. But I haven't thought about it.
Let's see.
Thank you. We still have some time for questions if there are more.
I think I have one more question. First, thank you very much for the talk. I really enjoyed it. And my question is, you mentioned other types in at the end of the talk, but I didn't quite understand. What's like the simplest? Next simplest case would be type C and cyclohedra. Do you have something similar for them, or?
But what we consider only the toric Schubert varieties in NED type. So then the type C. So we have
not cyclohedra, but central symmetric triangulations, something like that. Do they fit into the picture?
I'm sorry, I don't understand. So not Schubert varieties. You mean the? So
in the combinatorial picture, you have triangulations of a polygon.
Polygon, yes.
And which is counted by Catalan numbers, and
yes.
And say if you do central symmetric triangulations appear somehow in your picture, maybe for type C.
We haven't tried it. So we are wondering what kind of combinatory object appears in other types. So there must be some something nice, nice combinatory object which describes Bruhat interval polytope. So anyway, the generalization of our result to other types, there must be some nice object. So we are looking for.
Thank you.
But
Okay, more questions?
Yeah, I have a question concerning this particular picture which you show us right now. So this, I guess in this picture you took like two opposite points in permutohedron and took the Bruhat interval polytope, and it looks very symmetric. I don't know. First I thought that it may be a zonotope, but I guess it's not. But maybe you can say something about this class of polytopes which are obtained from opposite points. Yeah, I don't know. Maybe they have some nice properties. Yeah, that's just. It's an unformalized question, sorry. But this picture is very beautiful.
This picture, yeah, Sanchan drew this picture.
Okay.
All right. So if there are no more questions, then thank you again for the very nice talk. Thank you all for coming, for being active, asking questions, and see you next time.
It's nice seeing you all. Yeah.
Thank you.
Goodbye.